There was once a colony of ants. Okay? Do you know ants? Biologists know ants. There was once a colony of ants. Hmm? Ant hill. There was an ant hill. Okay? And they had gathered over the season some amount of, what do ants gather? Food. Okay, sugar. They had gathered sugar and they had some amount of sugar. Let's say that the ant hill had 7 grams of sugar. Okay? By and by, there was another ant hill next to it. And this ant hill had let's say 5 grams of sugar. Okay? Until here, 7 grams of sugar, 5 grams of sugar. Now these ants are red ants. Okay? Red is the color of danger. What else? Anger. Okay. Coming close to what I want. Blood. Coming close. Okay. The answer I'm looking for is caution. Okay. Answer I'm looking for is you won't get. Answer I'm looking for is communism. You are getting there. Red is the color of communism. These ants are communists. As the biologists among us will tell us, ants are always communists. Okay? What do communists hate? Inequality. Okay? So the ants decide the following. Out of our own goodwill, we will take 10% of what we have and we'll give it to our neighbor. Okay? Now here's the interesting thing though. They don't know how much the neighbor has. Okay? So what are they going to do? They are going to give whatever 10% of what they have, that anthill has, and give it to the neighbor. Since they don't know what the neighbor has, both anthills are going to do this. Okay? Calculate what happens after this process has taken place. Do it. Correct. But when I say calculate, I mean actually give me the answer. Very nice question. Is there an order to it? And what orders can you imagine? Okay. You see there's 3 possibilities here. So the possibility we are choosing is they compute individually. So they compute before any kind of transference has taken place. Okay? This happens, we are calculating for this happening once. That's a very good question. How many times does it happen? But we are calculating for it happening once. Okay? 6.8, 5.2. How many people got this answer? Anyone got any other answer? No? Everyone agrees? Okay. Simple enough, right? Okay. Prerequisites for this lecture series are addition and multiplication, okay? But we'll go rather advanced. I mean, prerequisites are simple. That doesn't mean the lecture series will stay simple, okay? 6.8, 5.2. What do you notice? 5 increased, 7 reduced. And so, did they achieve their goal? They're getting somewhat close, right? Which kind of makes his question relevant. How many times are they doing it? If they do it again, maybe they get even closer. Maybe if they do it again and again, and equality is achieved, who knows? So, yeah. Yes, 7 decreased, 5 increased. Anything more specific about this increase and decrease? Increase and decrease by the same amount? Yes. And that is what? Yeah, that's law of conservation of sugar, right? As the physicists amongst us know, there is a law of conservation of sugar which seems to be followed here. Okay. Anything else? How much sugar got transferred? 0.2 grams, which is 10% of the difference. Okay. Now that's obvious, but that's still interesting to note, right? Once you see it, it's obvious that that's happening. But it's interesting to note that they managed to transfer 10% of the difference from one to the other without ever communicating with each other. Okay. This is a very, very simple example of what is called a diffusion process. The term is not from signal processing, so you won't get questions on this. The term is from physics, right? Do you know what a diffusion process is? Where have you studied diffusion processes? What gets diffused? Perfume gets diffused, right? Correct? I mean, if I am wearing perfume, after some time it will get diffused through the entire classroom. Everyone will be able to smell the perfume, so it's getting diffused. Now, here is the question, right? The perfume was here to begin with. Now it's gone across the entire classroom. The question is, did the perfume molecules know that, oh, there's less perfume there, I should go there? They didn't know, na? Or did they know? Do they communicate by WhatsApp or something? How many perfume you have there? So then, how did they manage to go from an area of high concentration to an area of low concentration? We know that that's how diffusion happens. Goes from area of high concentration to area of low concentration. How do they manage to do this without having information about where the high concentration, where the low concentration is? And the answer is what we just saw. You understand this? Heat flowing from a body with a higher temperature to a lower temperature. Concentration going from higher to lower. All of this happens because basically you can actually do it without communication. Okay. We won't go too much into the details of the lower level of why that happens, because that would be a physics lecture. Then we are not taking physics. Okay. There were lots of anthills, and these lots of anthills had various amounts of sugar in them, as shown. Now it's a more complicated situation. Now anthill said, oh, more than one neighbors. What should I do? So anthills decided the following, that, for example, this anthill decided, I will give 10% of what I have to my left neighbor and 10% of what I have to my right neighbor. Both the 10% are computed at the same moment. Okay? And all anthills are going to do this. Transfer 10% of what they have to their left neighbor and 10% of what they have to their right neighbor. All anthills will do this. Is it okay? Question is, what happens at the boundary? Right? They don't have two neighbors. So can they follow the same rule? Yes. Let us assume, for the sake of mathematical simplicity, that there are infinitely many anthills on both the sides of zero wealth. Okay, zero sugar in them. Okay, so that's how mathematicians solve problems, idealize. Okay, what's the problem? 5 anthills, infinitely many anthills. Who's stopping them? Okay, so 0, 0, 0 here and 0, 0, 0 here. So the boundary problem doesn't exist. Okay, you get it? 5 numbers, 10% going left, 10% going right, remaining stays with me. What happens after the procedure is complete? Calculate. The specific question is what happens after one such operation. Otherwise, you are right. Called the heat death of the universe by physicists, but no, just once. Sugar death of ants. When you're done, raise your hand. I want the actual answer.
One question, the diffusion is happening only to the neighbor.
Only to the nearest neighbor. Yes. We could play other kinds of games, but right now we are saying only to the nearest. You have a question or you have finished? Okay, yes. Yeah, we can all sort out the answer. 0.4, 3.9, 6.5, okay. 5.0, 2.7, 3. What? It is 6.7. 3.7. Why am I hearing? This is what? That's why I'm hearing it. 6.7 and 0.8. I haven't calculated it, but all of you are saying the same thing, so we will trust you. Everyone has the same answers? Great. No? You got 3.6 here. Corrected? Right. Okay. Okay. So, we will introduce some notation. Okay. So, first of all, I am going to show the rule like this. 0.1, 0.1. Do you see the kind of notation I'm using? What should I put here? 0. Minus 0.2 would have been an option, but I'm going to say 0.8. Okay, which is how much you retain is how we will denote this. Okay, you see this? This is how I'm going to write the rule. 0.1 goes to the left neighbor, 0.1 goes to the right neighbor, 0.8 of what I owned stays with me. Make sense? Okay. This whole sequence of numbers here on the top ledger line, let me call it X. We are now being mathematicians. X. This sequence on the bottom line, let me call it Y. What are x and y? X and y are both sequences of numbers. Okay? X is a sequence of numbers. Y is a sequence of numbers. Is that okay, or is that an issue for someone? That's okay, right? I can give a letter to a whole sequence of numbers. If you have done some programming, it's like naming an array. Okay? Except that the array here has large size, extremely large size. That's our mathematical idealization. But it's kind of like that. Okay? If you are mathematicians, then giving variable names to sequences should not be a terrible thing. Okay. In terms of the lecture series that we are undergoing, a sequence of numbers is called a signal. Okay. So X is a signal and Y is a signal. First definition. What is a signal? A sequence of numbers. Okay, write that down. Okay. Once again, so X is a what? X is a sequence of numbers which we are going to call a signal. Y is another signal. Where does the word signal come from? I mean, the sequence of numbers is signaling some underlying reality. In this case, amount of sugar in anthills. That's where the word signal comes from. That is really quite strange, because any kind of mathematical object I could have called it a signal, right? Because any kind of mathematical object I could say that this is a representation of some underlying reality and called that a signal. But signal processing people captured the word signal, and now signal means this specific thing. Okay, so signal means sequence of numbers. This thing here, I will call it the, so okay, so this is signal. Let me write that. This is a signal. This is also a signal. And this thing here, I am going to call it the spreading rule. Okay. And let's give it a letter. Let's call it the spreading rule F. Okay. And the rule, specific rule F here says that you give 0.1 to the left, keep 0.8 and give 0.1 to the right. And this operation, this mathematical operation that all of you performed, I am going to notate it as follows. Y is X spread according to the spreading rule F. Okay. The signal Y is the signal X spread according to the spreading rule F. This symbol is my symbol for spreading. You can use any symbol. Symbols are arbitrary. We'll use this symbol. Okay. This spreading of a signal according to a rule to produce another signal. This mathematical operation has a specific name, and we'll now tell you that name. This operation is called convolution. Okay. What is the operation of convolution? Operation of convolution is taking some signal, spreading it according to some spreading rule to produce another signal. Okay, this operation is called convolution. It is important for lots of applications other than communist ant colonies, and we'll see why in the rest of this lecture series. This entire lecture series is about this operation. Okay, this is like some really trivial random thing to do, but we are going to see why this is one of the most important mathematical operations, and then we are going to see beautiful mathematical theory that applies to this mathematical operation and all the amazing things that come out of it. Let's do some fun things first. Huh? Okay. Look up. I am going to give you another problem, and you have to calculate again. I am going to make you calculate lots of things, and you have to do it. Okay. So I am going to change these numbers here, and you have to calculate the output. Ready? Do it. Who's done it? Already everyone's done it. What are the answers? Yes. Tell me a property that you would write in mathematical terms that we just derived for ourselves. Let's try not to use words we have learned outside. Okay. The only thing we are allowing ourselves is addition and multiplication. Everything we use only once I have said it. Otherwise, you all have very different backgrounds. So multiplication, he said multiplication. That's allowed. If a signal is multiplied by a constant, the output is multiplied by the same constant. Okay, that's the rule that we learned, which mathematically we'll note it as follows. I'll show you. Okay, kx star f equals ky, or how could I write it? K times x star f. You see? Do you see this? This, of course, this notation does require a little bit of I mean, there is a little bit of notation involved because this is not just algebraic multiplication. The k is a number, yes. But x is not a number. What is x? X is a signal. So kx is not really multiplication. Kx is an operation between a number and a signal, which we need a name for, and the name came from there a little while ago. That operation is called scaling. Okay? This operation here is called scaling. What is scaling? Multiplying every number in a signal by the same given number is the operation of scaling. Is that okay? And in those terms, now what have we proved? We have proved that scaling the input of a convolution scales the output of the convolution by the same scale. Okay? Okay. This property is called scale invariance. Yes? Yes. Yes. You can write it as ky. Yes, I substituted y equal to x square. Okay? I wrote it this way so that it makes sense even without the y. Okay? It seems like there's more characters here, but you can if you remember this, you don't have to prepend it with that other. Correct. It is ky. Okay? If you are of a little bit of mathematical persuasion, some textbooks, instead of calling it scale invariance, might call it homogeneity across scales. Or purely mathematically, they will drop the across scales and just call it homogeneity. Even though if you drop the across scales, that word doesn't mean anything, but mathematicians might call this property homogeneity. What it means is homogeneity across scales. The operation behaves similarly as you scale the input. The output scales equivalent. Okay? Is it okay? Right? And I mean, it's easy to see, right? One way to think about this is that here's a tricky way to think about it. If someone is not convinced, think about it as follows. You didn't actually change the numbers. Maybe you change the units of measurement. Instead of grams, maybe you are now measuring in decigrams. With the same reality, then the output measured in decigrams, it will have to be the same output, but just measure in decigrams, so the output will also scale by the same amount. Right? That's one way to think about it, just to convince yourself. Okay? Okay. Yes, but the output will be 4, 39, 65, 50, 37, 67, 8. Input becomes 10 times, output becomes 10 times. Similarly, if input becomes 2 times, output becomes 2 times. If input becomes 2.5 times, output becomes 2.5 times, and so forth. You agree to this, right? Okay. Many times, put in the correct light, things are intuitively easier to understand than to prove. One of the homeworks will ask you to prove this property, and you will see that it will take you a page and a half of writing mathematics to prove the property. But you do it as homework. If you don't have an intuitive concept of what is happening, then you have to depend on your proofs. Both should go hand in hand. You should be good at both. Okay, pay even closer attention. I'm going to make another change, and you have to compute the output. Okay? This is my change. Compute the output. Okay, how many people have the answer? Okay, nice. Okay, tell me, starting from here, this is 0.4, this is 4.1, this is 8.1, this is 5.2, this is 3.7, 6.7, 0.8. What did you do? Most of you, if you are used, I hope like you can do some sort of quick computation. What would you have done? Right, you just took this difference, right? There seems to be misaccounting, hidden wealth, recently uncovered, right? Let's tax it as well. Correct? And you said, oh, 2 more grams? Come on, give 10% here, give 10% there, keep 8% of that 2 more grams. Okay? And that's what you did. Correct? Added 10% of 2 grams, which is 0.2. Added 10% of 2 grams, which is 0.2 here. And kept 0.8% of those extra 2 grams, which is 1.6, which is what you added here. And that is how you compute. What general principle could we imagine ourselves as having used?
Plus convoluted L the same as convoluted F plus by convoluted.
Unfortunately, don't use Y. Yes, what is he is saying? W sign? Equals X star F plus W star F. Sorry. Sorry. Let me rewrite the whole thing. Even more? Can you see the K then? Sorry. X star F plus W star F equals X plus W star F. Okay. Now, again, this requires a little bit of explanation, because just like this was not multiplication, this symbol is not addition. What is this symbol? Now, X and W, I haven't told you what W is. W is another signal. For those who are not following, you will get it in a moment. Okay. X is a signal. W is another signal. And what does that addition mean? you add two signals element by element. Okay, that's what this addition symbol means. It's a special addition. It's a new thing that we are learning. Okay, adding two signals is adding them element by element. What are two signals? What are signals? Signals are sequences of numbers. Now I am telling you how to add two such mathematical objects. You add them by adding them term by term. Okay? Is that okay? And the addition of two signals spread according to some spreading rule equals the first signal spread according to that spreading rule added to the second signal spread according to that spreading rule. Okay? How is this related to what we just did? The extra 2 grams is another signal. What is W actually? 0 0 0 0 0 2 0 0 0. Okay? And so then this and what's you see that's W. 0 0 0 0 2 0 0 0 is W. And what's W star F? Correct. Is that 0 0 0 0.2 1.6 0.2 0 0 0. That's W star F. What's X star F? X star F is this thing here. And so if we are adding the input signals, then what will happen to the output? We'll add the output signal. That's how that notation relates to what happened on the board. Do you understand this? Okay. Now please understand, here we modified just one of them, but that doesn't have to be the case. Okay. Let us say all of them had hidden wealth. Okay. All of them actually, this fellow has, let us say +1, this fellow had this +2. I am now, the thing I am writing in green is W. Okay. So 7 + 2 is that 9 I showed earlier. This fellow has +1, this fellow has +4, +1, maybe all of them have hidden wealth. In which case, what will happen? To find the final answer, I can separately distribute the hidden wealth and I'll reach the correct answer. Okay? This property is called the superposition property or superposition principle. If you have a slightly mathematical bent of mind, you might call it distributive property. But signal processing book will call it superposition property, we'll call it superposition property. Okay? Scale invariance and superposition property are the two properties that we have studied till now of convolution. I hope you at least get the sense that they will be true of any signal, not just the signal showed on the board, and they will be true even if I change the spreading rule, not just for this spreading rule. Okay? Question? The question is, how do we add signals of infinite size? So here's the answer. If you are a mathematician, you somehow don't care about this question and you assume you can. Okay? Mathematicians can. You go and make them do it. Give them a signal of infinite size. And they anyway don't calculate. They say, we assume we can. So, mathematically, imagine that you can. Practically, there's two things will happen later on in the course. We will, in places, we will still assume that the signal is infinite, but the non-zero values are terminated because you want to compute it in a computer, right? So, for the sake of theory, we'll still assume the signal is infinite, but finitely terminated. And then the output could be larger, but we'll calculate the bounds of that as well and do some kind of data structure trickery to say that yes, this is also infinite, but there's only finitely many non-zeros, and we'll remember where the non-zeros are. Something like that is what we will do to work around that issue. Another part of the answer is that we will later on do all of this theory for more finite structures as well, which will apply directly to theory and to computing. So all of that will come later. Does that satisfy you for the time being at least? So short answer is yes, you cannot actually add infinitely many numbers. Okay, so this is a theoretical concept. Yes.
Because the way I'm thinking about it, if there are like thousands or like millions of zeros, storing it in a computer will be called unnecessary. People who are recording this, they will have an
Correct. And so which is why the first part of my answer was that practically we will have to learn to deal with it in a programmatic fashion, which we'll learn to deal with. I mean, if you think about, we are dealing with it right now, aren't we? We have a finite bore. We're talking about infinite signals. We're dealing with it. Same thing you do in a computer, you're dealing with it in a programmatic fashion. Okay. So, right? Yes.
plotting it over x, y,
Yes.
addition of functions is different. So addition of functions is like
So now you're thinking like a mathematician, right? Addition of functions is defined. Right. And yes, that's what I mean by thinking of, you're right, you're not wrong. You did it in closed form. Right. And you'll say that I did the addition in closed form. That's fine. Did you actually compute every value? No. You presumptively computed every value. Right? Yes. What do you mean?
y sine of
Y as sign of? Okay. So let's not use the word that you used because that's not defined in the lecture series till now. But the spreading rule is always going to be yellow lines. Don't have to be yellow, but always going to be lines with numbers on them. So I'm not going to allow you to say sign of something in the spreading rule. Okay? It's going to be some percentage. Yes. Okay? So spreading rules are limited to having lines and percentages on them. Okay? These two properties together, these two properties occur so frequently together that mathematicians gave them a name. They are called linearity. Linearity. And we'll learn more about what that means mathematically in some later lectures. Yes?
I know this is a little off topic, but the f in the convolution that we talked about, it's kind of like a function. Like, think of it like a function.
And what will you, where will this go?
So I was asking whether it only works for linear functions, scale invariance property only works for linear functions, or does it for
The rule F always has lines going in different directions with numbers on them. Okay? That's all the kind of rules F that I allow. There is, here I refuse to say linear or non-linear when speaking like this. So I'll not say that. Then we said for such a rule F, these two properties are true. These two properties together have a mathematical name called linearity. Okay? Before going into the break, can I give you a very nice example? No more calculations, but I want to give you a very nice example. Can I give you a very nice example? So, here when we talked about signal, it is a sequence of numbers. And what are those? Why are they in a sequence? What is the sequentiality? Where does the sequential nature of those numbers come from? Why isn't it just a collection of numbers but a sequence of numbers? Can you tell me? Order matters because they are neighbors. So, because of their spatial position, space-based position. Okay? Okay, we'll call such a signal a space-based signal or a spatial signal. S-P-A-T-I-A-L. Spatial signal. Okay, not special, spatial. Okay? Many a times in many applications, signals are not space-based, but they are time-based signals. Time also has neighborliness, but not like space has neighborliness. It's a different kind of neighborliness. What are neighbors in time? Yeah, moments that are close in time are neighbors in time. Okay? So, what would be a time-based signal? Acoustic data could be a time-based signal. What is acoustic data? I am speaking right now. Is that a time-based signal? I am speaking, right? Talking, acoustic, sound. Is that a signal? Why? Where's the signal? What is the signal? Word has not been used.
That you can use to quantify
What is that number? Here it was amount of sugar in grams. What would be that number? Decibels is wrong for a specific reason. Pressure actually. Okay. It is actual air pressure. Okay, actual air pressure measured in Newton per meter square. Right? I'm not a physicist. Am I doing this correctly? Pascals. Was that also right? Okay. Okay. Now, please understand this. In a time-based signal, if I were to write it out as a sequence, what is the time axis? This is the time axis. Okay. So, if let us say I am speaking something, standing here speaking, right? You get pressure. The pressure of air, let us say 1 millimeter outside my mouth, is changing. That changing pressure has changing values. The values are changing in time. If we write that down as a sequence, that becomes a signal. This axis, which is space, the same axis will be time in that application. Okay? See why I stopped you. Okay? Now, can you hear what I'm saying? Can you hear what I'm saying? Can you hear what I'm saying? Really? Can you really hear what I'm saying? What are you actually hearing? You imagine you hear what I'm saying. What do you actually hear? Do you sense the sound pressure level 1 millimeter outside my mouth? You are hearing something else. Now tell me what you are hearing. The sound pressure level in your ear. Which ear? Let's fix 1 ear so that we have one output signal. Which ear? What is left ear and said right ear? Okay. There's only 50% chance of. Okay. So, here's the left ear. Okay. His left ear, is his left ear actually sensing the sound pressure level being produced by me? No. What is it sensing? Yeah. Sound pressure inside your ear. Correct? 1 millimeter outside his ear. Sound pressures 1 millimeter outside his ear. Which is a signal. But is it the same signal? Not the same signal. Then what is it? Let's think about it. Let's think about it. The sound emanating from my mouth reaches his ear. Are they the same pressures? No. The pressure drops. You must have done a little bit of it, or I mean, just by intuition, how much ever we know, we'll accept it, right? So, the same sound pressure will not reach his ear. I'm literally shouting to reach that fellow. If I shouted 1 millimeter outside his ear, what will happen? He'll go deaf. He's not. He'll drop the course, which is still we don't know about that. Right? So, he's clearly hearing something else. So, what is happening is the sound that starts at my mouth reaches his ear, but not the same level, at a diminished level. That's not the only thing. What else? Something even before that. Does it reach at the same moment? There is a delay. There is a delay, right? You know enough to know that there is a delay. There is some amount of delay. What else? Let's forget the other noise for the time being. There are still other things about how my sound reaches his ear. Yeah, all of those are important. Something that's actually more important. Time has shifted, but we already spoke about that. There's a time delay. Okay. What about the wall there? What is the wall doing? Reflecting the sound. Is it reaching his ear? Yes, it is reaching his ear. And what is happening? Is it at the same volume? It's at even another different volume. Same delay? A different delay. So, my sound is reaching his ear in two ways. At two different volumes and two different delays. Is it two ways? There and there and there and back and here and then bounce and then his ear. Bounce and his ear. Bounce and his ear. Lots and lots of different things are happening with my sound, the sound I am producing reaching his ear. So can he hear what I'm saying? He hears a completely different thing, doesn't he? Completely messed up and completely smudged. Can you hear what I'm saying? What you hear is messed up in a different way. Each of you is receiving a different lecture, believe it or not. Okay? Okay. Quickly, see, instead of these ant hills, imagine that these are sound pressure levels and this is the time axis, correct? This is time. And these are the sound pressure levels. And then these are the received sound pressure levels at his ear. Now, if let's remove the additions here, we don't need all that complexity. Suppose I produced a sound pressure level of 4. What effect does that have? Right? There's a direct effect. The direct effect has some volume diminishment and some delay. How do I represent it here? Nice. I show it like this and then I say maybe, I don't know, 0.2. Okay? There's also reflection. Reflection has even lower volume, even more delay. Okay? So maybe it is 0.1 more delay. There's another reflection and there could be more reflection. Now, whatever is happening to this sound pressure is happening to every sound pressure. Right? Right? The sounds are produced sequentially. The pressures are heard sequentially. The delay is the same. As the time index here goes on increasing, the time index of receiving also goes on increasing. The delay remains the same if both of us don't move. Okay? When we move, delay changes, which is why his spreading rule is different. You see this? Do you see that transmission and reception of sound is a convolution? Okay? And actually this convolution is so harsh and the smudge that the convolution causes is so harsh that actually what I speak ought to be indecipherable to him and to all of you. But you can all hear what I am saying because of some amazing theory that we are going to learn in this lecture series. I hope I convinced you that convolution is important. We are going to take a 5-minute break, do a few more properties. After that, take a break, go out, come back. Let me give you a quick problem. I'm going to give you this problem. Okay, now the time is gone. We are back to ants. Okay, I love ants. Here with me. That's the problem. That is the input. Okay. Forget the input here. Just that is the input. What is the output? Correct? Yes? Seems trivial, but what did we learn? Yes. If you put in an input of all zeros except 1, 1, then the output will actually be a readout of the spreading rule. Right? I mean, if you were the god of ants, but you didn't know how ants behave, biologists will love this. They think they are the gods of their subject. Right? If you are the god of ants, but you don't know how ants behave. How God behaves in reverse. Okay. If you don't know how ants behave, what will you do? Correct. Take away all the sugar, give 1 gram of sugar to one anthill, see what happens. The output that you will get will be the spreading rule of the ants. Okay? Such a kind of an input is called an impulse input. Okay? Technical term. Impulse input. The corresponding output is called the impulse response. Make sense? Impulse response. Okay? And so, the spreading rule, what did we just learn? That the spreading rule equals the impulse response. Okay? Now this is a little strange. I just said equal to. How can it be equal to? The impulse response is a signal. What is the spreading rule? I have avoided defining it too much till now, but now let me make it precise. The spreading rule is also a signal because it also is a sequence of numbers. Okay?
Yeah, so the spreading rule, is it dependent on the index? Like, can we using the spreading rule as an independent of index? So for all indices, I'll apply the same spreading.
It is the same spreading rule that all indices will have.
a variable thing? Is that a thing?
That's not a thing.
It's not.
It's not a thing. And I will explain one later lecture what all of that means, but it's not a thing. Okay? Okay, this is okay. Spreading rule is the impulse response. In fact, I mean, the book won't even call this a theorem, even though it is a theorem. The book won't even call it a theorem. The book will just call the spreading rule impulse response. It's such a triviality that most books won't make a distinction between these two and just call this the impulse response. And later on, I might as well start calling it the impulse response, but I'll try to keep on calling this the spreading rule. Okay? One simple thing that we learned. Let me ask you a question. Out as well. Why not to confuse ourselves? Calculate the sum of the output. Calculate the total sugar on the bottom line. Raise your hand when done. What was the trick? You calculated the sum on the input. Correct? Why? Law of conservation of sugar. Correct? So, what did we learn? The sum of the output equals the sum of the... Is this always true? Why did it turn out to be true? Because the spreading rule adds up to 1. So the spreading rule is fully efficient. Right? It's not lossy. These are not technical terms. I just came up with it. Don't have to write it down. Right? What if the spreading rule had this instead? Will the sum of the output still be the sum of the input? What will be the sum of the output? 0.9 times the sum of the input. General property.
About the impulse response, by
No, there's not. Okay. Spreading rule. Spreading rule.
by the signal, the sum of the signal will give you the sum of the output.
See this? Sum of the input multiplied by the sum of the spreading rule equals the sum of the output. Correct? Let me just mnemonically write it as sum x, sum f equals sum x star. Correct? Is it okay? I didn't show the indices and so forth, but let sum x is the summation of all the numbers in x. Sum f is the summation of all the numbers in x. Correct? So again, when f itself added up to 1, the summation of f and the summation of x star f was the same. Correct? So this and this were the same. But when this was a different factor, then these were not the same. This is okay? No? We are going to revisit this later on. So if this is a bit complicated, you don't have to worry about this too much. This is, if this needs a name, it's called the strength theorem.
Might make the clear understanding the theorem a bit simpler.
Explain.
So let's say that the impulse function had a vector of zeros, and in one place there was a 1. And then we used the spreading function and became 0.1. In the impulse response, it became 0.1, 0.8, and 0.1. Correct? So now what the theorem here that you're written is stating is that summation x into summation f equal to
X star f.
x star.
X convolve f.
X convolve. Summation x will be here 1. And summation f will be 1. Summation, no, impulse function.
Correct. Summation x will be 1. Summation f will be 1. Correct.
So 1 into 1, 1.
Yes.
Here x into f will again be 1.
Yes.
So 1.
Yes.
But now if it was this thing, 1 into 0.7 into 0.1, then it will be 1 into 0.9.
Yes.
Correct?
Yes.
Which
and the impulse response will also be 0.1, 0.7, 0.9. So the impulse response will also add to 0.9. So that's what will happen. Correct. So you're right. So with this is a more general statement, but anyway, I am giving examples. So he's giving other examples. So it's okay. So yes, it works even when you don't have just impulse inputs, is what he is trying to say. Right? Yeah, I agree. Okay. There was once a colony of ants, and these were black ants. Listen to me carefully. Last part of lecture. There was once a colony of ants, and these were black ants. If red ants are communists, black ants must be capitalists. Right? What did I say? Communism, capitalism, you know? Do you know? Yes, you know. Yeah. Black, evil, capitalists. What do they do? Hoard. Not just hoard. No, don't tax. Communist tax. Come on. Oh, yeah. Steal. You got it right. Black ants steal from their neighbors. Okay. Now they don't give out their wealth. No. What do? They steal from their neighbor. Okay. But they are conscientious thieves. चोरों के भी उसूल होते हैं. Okay? Conscientious thieves, they go to their neighbor, take 10% of what the neighbor has, and come back. Okay? Not 10% of what I own, 10% of what the neighbor has. So, 10% of what the neighbor has. 10% of what this neighbor has. And they'll continue to own what they own, right? No. Why? Neighbors are also thieves. So what is happening? At the same time, they went and stole from their neighbors. What are their neighbors doing?
And then stole it from them.
Came and stole from them. So let's say that they stole extremely simultaneously. Both of them stole 10% of what these people owned initially. So what do they continue to own? 0.8. So very different economic system. Calculate the output. Raise your hand when done. Yes. Yes. Yes, they do have the information now. Yes, you're right. Yes. So which is why I said they go to their neighbors, they account all, they go there, do the accountancy, find all their wealth, take 10% and leave. So information is needed. You're right. Yes. Yes. Who has the answer? And what is the answer? It's the same answer. It is the same answer. Communism equals
Either you are giving away sugar or someone is taking actually sugar is
correct. Okay, let us be a little bit more precise about this. Suppose my spreading rule was, let us say 0.1, 0.2 and 0.7. Okay? Lopsided communism. Give to thy neighbor, but give more to thy neighbor on the right. Okay? So give 20% to the right neighbor, 10% to the left neighbor, own 0.7% of what you owned. If this was the communism rule, what would be the equivalent capitalism rule which would have the same effect? You see this? The equivalent capitalistic rule would be to steal 0.2 from the left neighbor, 0.1 from the right neighbor, and continue to own 0.7 because 0.3 got stolen from you as well. Okay? Correct? We are going to give this thing a name. This was called the spreading rule. We will call this the gathering rule. Okay? Spreading rule, gathering rule. For every spreading rule, there is a corresponding gathering rule. And what is the corresponding gathering rule? Yes, absolutely. The gathering rule is the flip reversal of the spreading rule. Correct? Okay? whatever you would have given to your right neighbor, you steal instead from your left neighbor. Correct? This will work even if it was more than 3. I mean, even if you had more distant neighbors, the gathering rule would be the flip of the spreading rule. Okay? In the acoustics example, let's see how this works in the acoustics example. What I say is heard by him, let us say 7 milliseconds later, then again 13 milliseconds later, then again 18 milliseconds later. What I say is heard by him in echoes. That would be the spreading rule. What would be a gathering rule? That has the equivalent effect. In fact, both of them are happening. There is no communism, capitalism. Both of them are happening. What is the corresponding gathering rule? What he hears at a particular moment is a mixture of what I said 7 milliseconds ago and 13 milliseconds ago and 18 milliseconds. One coming direct path, one coming some reflection, one coming some other reflection, and so forth. And the gathering rule will be the exact flip of the spreading rule. Okay? Is okay? And we are going to use this idea to create a mathematical formula, or let us say a program for calculating convolution. We have been doing it informally, but now we will have a nice looking program or formula. Okay? Now this is going to take a little bit of notation. So follow along. Last part of the lecture today. This is a sequence of numbers, right? That sequence is called X. Okay. Now, let me give mathematical labels to the individual values in that sequence. I am going to say I will call this X minus 2. And I will call this X minus 1. I will call this X0, let us say. I will call this X1, X2, X3, X4, X5, so forth, right? And there's X minus 3, minus 4 also to the left. You might say, why am I using negative numbers there? Well, it's infinite on both sides, so I'll have to use negative numbers. Okay? Fine? Correspondingly, the output, I will call this at the same index, whether it's space index or time index, I will give the same index inside the bracket. Okay, this is a new mathematical notation I am creating right now. Brackets means what? Bracket means this operation, the index. Do you understand what is y minus 2? It's just the value 0.4. Nothing very scary about it. It's just a number. Okay, it's scarier in mathematical notation than its actual number. It's just a number. Y minus 2, y minus 1, y0, y1, y2, y3, y4. Okay. The spreading rule, I am going to give it names as well. I am going to say that this is f of 0. I will call this f of 1. And I will call this f of minus 1. You see how that's also a sequence. If I had more lines going to the right or left, I would give them the same kind of notation, right? Same kind of bracket notation. Okay? And so if that is the case, then what is happening in the gathering? The gathering is going to flip the spreading rule. So what does the gathering, now what is this line? F of 1. And this is f of 0. And this is f of minus 1. See, what is happening in the gathering is that the indices are flipping. Indices to the right are negative. Strange, but that is what is happening because our indices are based on the spreading rule. Why are indices based on the spreading rule? Because we want the indices of the spreading rule and the indices of the impulse response to match. Okay, that's why we created indices based on the spreading rule. But in the gathering rule now, the indices are flipped. Okay, this is okay. And now, if I ask you, what is the formula to calculate y of 1, let us say. Write down the formula to calculate y of 1. Do it. Y of 1 equals x0 times f1 x1 times f0 f2 times f minus 1. Is it okay? Is this all? In general, we shouldn't stick to just 3 lines, right? In general. And so there could be here, there could be what else? There could be x3 times f minus 2, correct? And on the left, you could have x minus 1 times f2, and so on and so forth on both the sides. Is this okay? In general, yes, we are coming to that. In general, what is the rule for y of n? Let's calculate that. Same thing, but just do it for any value n. So it will be, so here what will be this value here? xn f0, correct? xn f0. Okay. If you are saying off, that's okay as well. I might not use the word off, but I mean the same thing. X of n is also a correct way to say this. xn f0. What will go here? Right? 1 anthill to the left. So xn minus 1. And this line, which is f1. Why f1? Because the rule is xn f1. Sorry. xn minus 1 f1. And here you have x n plus 1 f minus 1. And so on and so forth. Okay? On both the sides. Correct? And now let's collapse this further. Y of n equals, let's write it as a summation and let's write it clearly, right? Like true mathematics.
I belongs to it.
X of n minus I.
K. For some reason it's K. K belongs to integers. Okay. Yes, same as k belongs to integers. I like that version better. Both are okay. But x of n minus k f of k. Okay. Okay. This is okay. This thing is called the convolution formula because that's the way to compute any convolution. In fact, in any signal processing book or any signals and systems book or lots of books, this formula will come first as the definition of convolution. And then all the theorems that we do today will come as theorems proved using this formula. It's the right way to do it mathematically, so the homework is going to ask you to do it in that fashion. Okay? I cannot stress enough how important this formula is. I do not have the tools yet to tell you why convolution is such an extremely important operation. But right now, with whatever examples cooked up or possibly a little bit realistic transmission and reception of signals that I gave you, trust me that convolution is the most important operator that you will face if you are a physicist, if you are a biologist doing dynamical systems, if you are a chemist doing reactor physics, if you are doing anything at all, convolution is the most important operation. If you are doing machine learning these days, convolutional neural networks, heard that term? Yeah. So why are they using convolution? Because it's the most important operator. We are going to learn some absolutely beautiful theory regarding convolution. And it's going to take us to this strange, wonderful realm called the frequency domain. We are going to learn what this is, frequency domain. We are going to learn what is the concept of a Fourier transform, the Z transform, variant of the Laplace transform. We might hit a little bit upon the Laplace transform and why all of that is important and how that is fundamental to analyze any kind of, physical or artificial system is something that we'll learn throughout this course. So what we learned today was the operation of convolution. Now finally with the mathematical formula and some theorems about convolution, including the superposition theorem, the scaling theorem. Both of them together are called the linearity. The strength theorem, and the fact that the scatter and the gather are reverse of each other. We also learned that the spreading rule equals the impulse response. So that's it for today. If you enjoyed, I hope you continue watching. Do like, share, and subscribe by coming next time to the lecture. Thank you very much. Bye bye.